this off.
So first thing you guys want to learn is what's inside a computer, like the actual parts of it, the hardware. Main first thing is the motherboard, which is a big green plate you see at the front. What it does, it holds all the important components of the computer, such as the CPU, RAM, and expansion slots. So the CPU is like the core of the computer. It does all of the calculations for like all the calculations, and then it requires a heatsink because it creates a lot of heat. So the heatsink is used to bring heat away. The RAM is for like holding short-term memory, and then when you want to hold long-term memory, it's from the hard drive, which is on the left bottom left. Next is the expansion slots. So these things, those three bars on the bottom of the motherboard, they can attach things like a GPU or sound cards that will help your computer get faster or have better sound quality. And then finally, the power supply, which obviously powers your computer. Next slide. So this is just a list of the main parts of the computer, which I said were motherboard, CPU, memory. And then you can also have ports for like a CD disk, and then expansion slots, and then this system clock thing. Next slide. So now it's the extra parts of the computer, which are the hard drive. There's two types of hard drives. There's two types of hard drives, and then solid state drives. They both hold long-term storage, but solid state drives are faster. Then you have optical drives, which are like CD disk, and then input output devices, which include input is like things that you can put into your computer and tell it what to do, like keyboards, mouses, microphone, camera. Output is what the computer shows to you, like display and sound. Then you can have communication devices like Wi-Fi adapters. Next slide. So the three most important parts of the computer, though, are the CPU, because it processes all the calculations in the computer, and then the memory, which is temporary storage, and then finally hard drive, which is the permanent storage.
So the CPU, it gets all its instructions from the memory, which is the RAM, and so the RAM is relatively small, but it will store all the instructions and data inside a stack, and so the RAM will access all of its instructions and all of its data from the hard drive, which is your mass permanent storage where all your files, everything is stored.
So basically, a computer is a complicated electric circuit. You can turn it either on or off. One example that all of you have probably heard of is the light bulb circuit. You have a light bulb, a battery, wires, and an on and off switch. So what exactly is an electrical circuit? If you see in the picture, we have an atom which contains electrons. Wait, where's the other slide? Slide before. Yeah, okay. So we have an atom which contains electrons. Electrons are the negatively charged particles. So when electrons move from atom to atom, it creates a flow of charge. So this charge is called electricity. So there are two stages of an electrical circuit. On the right, you can see when the switch is closed and the circuit's on. This represents a binary 1. You can also see when the switch is open and the circuit's off. This represents binary 0. You should remember this. So what are digital signals? Wait, this is... Okay, yeah. So what are digital signals? Digital signals are continuous streams of alternating rising edges or falling edges. So this represents a binary number or an encoded character. So two questions that we have is which number does the above stream of zeros and ones represent? And how about which character? Remember these questions. Wait, I think you skipped this slide. Okay. So there are different types of number systems. Base 10 decimal, base 16 hexadecimal, and base 2 binary. So using the digital signal shown below, we could get 76 for base 10 and 4C for base 16. So there are 16 numbers in base 16, but we only have 0 through 9. So we use letters for the rest of the numbers. A is 10, B is 11, and C is 12, and so on. The digital signal is divided up by bits, and 8 bits is 1 byte. Memory is just a long sequence of bytes, numbered 0, 1, 2, 3, and so on. So the answer to the previous question was the numerical value of 76, or the capital letter of L. Okay, so this is an ASCII table. It's a code for representing English characters, such as like letters and numbers. Each character is assigned a number 0 through 127. Computers use ASCII codes to represent text. So through this, data can be like transferred from one computer to another. You don't have to remember this, but it's just a cool thing to show you. So a computer can process a binary data, So a computer can process binary data, numerical or characters in the form of digital signal. So a part of what a CPU does, as mentioned before by David, is binary calculations, so math. So how does it do binary calculations? So an example here is shown below. So when you add up the 1 and the 1, you get a 0. Think of it as like a 10. You have to put the 1, you carry the 1 back up. So whenever there are two ones in the same column, you carry the 1 back up.
And so each of these positions down here represents a power of 2. So this position is 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and so on. So switch states. So we need to understand how the computer can recognize binary. So going from on to off represents going from binary 1 to binary 0. And same vice versa, going from off to on is going from a value of 0 to a value of 1. So normally, as seen in this picture, we normally turn the switches on and off by our hands. But how would a computer be able to turn it on and off? So there's a couple ways that the computer can turn this switch on and off. So there's a vacuum tube, there's a relay, and there's a transistor, which is also known as a semiconductor. So a vacuum tube. A vacuum tube is electrical switch, which is controlled by electrical digital signals from another circuit. So this is a diagram of what it would look like. Next is a relay. So a relay is electrical switch, which is also controlled by electrical digital signals from another circuit. So as you can see here, here is the electrical digital signal that is going to be controlling this magnet over here. And so when this circuit is a closed loop, then this magnet will activate. And so this switch over here will then get pulled towards this wire over here, and this will form a closed circuit as well. So that means that this lamp would then light up. Transistor, also known as a semiconductor. And so it's an electrical switch, and it can be controlled by electrical digital signals. So this is where the semiconductor is going to be located. So the most common semiconductor we know of is silicon. And so this silicon, it can change its conductivity based on the electrical digital signals that it receives. So bootstrapping. So bootstrapping of one circuit allows it to control the output of another circuit. So this allows us to create logic gates. And so this is what a fairly complicated logic gate would look like. So in order for us to evaluate what is happening in this logic gate, we need to know what all these symbols mean. So all these symbols are part of boolean algebra. So boolean algebra was invented by mathematician George Boolean, which is why it's named boolean algebra. And so the three basic functions of this are and, or, and not. And using these three, we can create all sorts of combinations of commands, including XOR, NOR, and NAND. And so in order for us to find out the output in an organized manner, we can use a truth table. So Boolean logic. So AND is, so a safe deposit is kind of like an AND gate, where you need both keys in order to open up this one drawer. OR is like your home entrance, where you only need one key in order to open up the door. And not means that an example could be like a whining kid who won't change his mind. So Boolean logic can very easily be represented using a Venn diagram. So over here, the Venn diagram can represent AND in this small shaded area over here. OR is represented by either of these two circles, including the between region. NOR is the literal opposite. And so everything outside of these two circles includes NOR. And XOR, or exclusively OR, means OR but not AND. So both these circles without this shared region. So the NAND logic gate. NAND can be made using NOT and AND. So this is what the AND logic gate would look like and what the NOT would look like. So combined, this would create NAND. So NAND is the reason why it's so important is because it can be used to create all of the other logic gates, including XOR, which this example shows over here. So transistor to transistor logic. So the Boolean logic gate circuit, or the electric implementation of the Boolean logic gate. so over here we have and so as you can see, this electrical circuit, it can be represented by these transistor switches. Not over here, it can be represented using this transistor switch, and so the output is immediately reversed. And the OR logic gate, in which either one of these values needs to be 1, and so the output would then be 1. Does anyone have any questions? Uh, you can unmute yourself if you have a question. No questions? So I guess we can go back and just make sure that we have a solid base on this.
Okay, so this slide was skipped, so let's get back to it. So what are signals? So this is the Google definition right here. The most important parts are bold, are in blue. So signals have two states, a long or a short pulse. With these, you can use Morse code, as you guys probably have heard, to communicate in numbers or letters. There's a picture of Morse code on the top right.
So Morse code is what sailors used to communicate each other through those submarine telescope looking things. So these are digital signals. So digital signals is a continuous stream of alternating, and so this can represent a binary number. So it's important that we know this because this bit over here, this byte over here actually, can represent more than just one thing. So if we look over here in the ASCII table, and we look at the value of 76, we can see that it it represents not only the number but also the letter L. Anyone have any questions? Still no questions? I guess we can move on then. Okay, so Boolean logic and binary addition. So binary addition is not very intuitive. And so here's a pretty simple example. We saw this earlier in the presentation. So in which gate would we carry over this one? Can anybody answer that?
When you have two ones.
So the AND gate, right? So only in the case of the AND gate, where both of these values are 1, will we carry over this 1. And so the value in that digit slot will be a 0. So as you can see in the output over here, the output will only be 0 if they are both 1 or they are both 0, and it will only carry if both of them are 1. So the half adder. So this is a little bit complicated. So a half adder will add 2 binary digits, and it will not take in the account of a carry from a previous digit. So essentially, it will only have these 2 inputs, and its output will be the number that these 2 were added and the carryover. So here's the half adder in the truth table. So as you can see, we can look at all these inputs and we can see the outputs that it creates. So essentially, this half adder is only accurate if there is no carry from previous digits. So now that we've looked into the half adder, now we can look at what a full adder would do. So can anybody guess what a full adder would do? Nobody? Okay. So a full adder will take into account the carry. So that's where C in comes into play. So C in is essentially the carry in. So if we have over here uh, a 0 plus 1. So normally 0 plus 1 would create an output of just 1, which would mean that the value of S over here would equal to 1. However, since we have a carry in from the previous digits, then that means that the value of S will be 0, and instead it will carry over to the next digit as a 1. So we can look at this truth table over here, and so it starts getting a little more complicated with the full adder. So 1-bit arithmetic and logic units. So 1 bit would be this column over here. So this cell can be add, and, or. So this is what the diagram would look like, and so this is what the truth table looks like. So essentially, this is very, very similar to a full adder. So the 1-bit arithmetic and logic unit relating to all 4 operations. So the basic operation is adding 2 things together. And so using this one operation, we can create subtraction, multiplication, and division. So subtraction is essentially addition of negation. And so you're just adding a negative number. Multiplication is just adding multiple times the same thing to itself. And division is essentially just subtracting multiple times. And so a 1-bit arithmetic and logic unit, a full adder with this with some of the logic circuits, can do all 4 of these mathematical operations, even though some of them might be a little complicated. Daniel, you have a question? You can unmute yourself. So division is, in super simplification, it's subtraction multiple times, with a carryover. So you want to see how many times you can subtract yourself until you can no longer subtract it. And so you will get that's where the remainder comes in. And so if we go into any programming language, and you do division, it will always round down. And the reason why it does that is because it will it will omit the remainder, and instead it will just return the number of times you can fit that number into the uh, the number you're trying to divide it. So a multi-bit ALU. So we saw a singular bit. So now if we look into a multi-bit, we can have 32 and 64 bits. So this is multi-digit binary calculation. So if you looked at the single bit ALU, we could probably do that ourselves pretty fast. But once we get into these larger numbers, it's going to be much, much harder for a human to outcalculate a computer. So if we look over here, we can see how a multi-bit ALU would work. So essentially, we have four 1-bit full adders over here. So this is essentially a 4-bit ALU. And so we take in 4 separate numbers, and so they're getting added together. And so it will create it'll also take in the carry in, and so it will produce a carry out, and it will produce its output. So CPU. So essentially a CPU, David, you want to explain this?
Yeah, okay. So CPUs have multiple cores that can do the same. They can do multiple things at a time. So the more cores, the more multitasking the CPU can do. And then the CPU has a memory controller that controls, obviously controls memory. So then it has L3 cache, which I'm actually not really familiar with. Do you know, Matthew? Because I'm not really sure.
Um, so this is not as important, but if we look into CPU, so essentially the main point of this slide is to tell you that the CPU is where all of the ALU calculations, all the bit calculations occur. So I'm not sure of the exact number, but it can do a lot of calculations at once. And of course, that depends on the number of cores that are available. So in summary, so we went from the atom or electron to the electrical circuit. And so we saw how in the electrical circuit that there was an on and off state, which led us to the digital signal with a switch. And so from the digital signal, we figured out how the computer would control it using the transistor or a semiconductor or relay. And from the transistor, we went to Boolean logic. So we could see how we can manipulate it using this Boolean logic. And then from our basis of Boolean logic, we saw how we could use logic gate circuitry in order to create more complicated logic gates. And from these more complicated logic gates, we saw how we could create a simple binary adder. And we went from a half adder to a full adder. And then we saw how the single bit ALU works. And then we saw the 32 bit, and so the computer can also do 64 bit. And so that shows us how the computer's brain or the CPU works. So the CPU mostly just does the binary computations and these logic operations. And so when you run your computer program, that is essentially what it will all do. All those words you type, all those characters you type, it will all be converted into binary. And so that's how the computer will give you an output. So slightly more advanced view of this CPU. No? Okay. So that will wrap it up for today. Anybody have any questions? No questions? Do we want to do some questions?
So guys, if that was pretty that was a pretty lengthy presentation by the 99098 team. Basically show you how the computer CPU actually work. And so eventually why this is useful information is because when you do the programming, and you might wonder how you program it actually get the executed by the computer brain, the CPU. So hopefully this will give you a very rough idea. Obviously, many of the concepts are pretty advanced, so it will take you some time to think through, understand. And you probably have any doesn't have any questions for now, but I highly encourage you to go through the slides and think through and to see does any of this make any sense to you. So to really just summarize, okay, and all this thing is really telling you is that the computer, like the name implies, it computes, and it computes in the binary term, 0 and 1s. And because those are dictated by how the electric circuit works, because they don't have one on and off, two states. So once you understand that part, right, and so everything else sort of fall into place. I would encourage you guys to ask, any question. There's no question that's silly or stupid, right? Because we all learn here. So anybody, any question at all? Okay, so if no question from audience, I'm going to ask a question, and so let's see if anybody can provide an answer based on what you're understanding from this presentation. Okay, so we talk about a lot of things here, and one particular thing that's in my mind is quite important is the Boolean logic. And can anybody tell me why is it important to understand all this? Like, why would we talk about some kind of Boolean logic when it comes to computer stuff? Anybody? Anyone can give a shot to that question?
The computer uses the Boolean logic to do all its calculations.
Okay, that's good. Do you guys think that's a good answer? Okay. So yeah, I highly, so basically, in order for this to be a good teaching sections, right? I highly encourage you to be, don't be shy and ask questions and make it a highly interactive process. So I think, Matthew can take us away and to basically conclude this presentation. But, again, right, so if you guys have any other questions, I encourage you to email, the host, right, with the questions. And once we get the questions, and then the team will basically reply back with the answers. All right, Matthew, want to take it back?
Okay, so as Coach said, today we went over how the computer computes in binary. And so it's not necessarily like necessary to know this, but it's kind of cool when you think about it, how your entire computer program can be simplified into this really simple, all these simple binary calculations, except there's obviously a lot of them. So next class, what we're gonna do is we're gonna go over how to like set up Python and stuff, and so we're gonna continue giving a base on how programming works, and kind of a calendar on what's gonna happen in future classes and exactly what we're gonna learn about Python. So any final thoughts? Well, I guess thank you for listening to us, and you guys are free to go.
Yeah, thank you guys. See you.
Yeah, bye. Thank you.
Thank you.